Welcome back to differential equations. In section 4.4, we will learn derivatives, integrals, and products of transforms. These are properties that we will learn about Laplace transforms that will help us to get back to solving those initial value problems. We begin with the convolution property. Definition: the convolution f star g of the piecewise continuous functions f and g is defined for all t greater than or equal to 0 as f star g of t equals the integral from 0 to t of f of tau times g of t minus tau d tau. Now, the formulas just keep getting more and more complicated as we progress through chapter 4. So let's stop and talk about the details of this formula. First of all, we are dealing with a binary operator. The symbol between the f and the g, the star symbol, represents this operation called convolution. Now, I remember being an undergraduate and studying differential equations, and I had a professor with a beautiful Indian accent, and I will never forget listening to him talk about the convolution property. I can still hear his words in my mind. The convolution property, again, is a binary operator, and that symbol codes instructions for a specific way of combining the two functions f and g. So when I see that binary symbol, it represents this integral operation. Now, we're going to find the integral from 0 to t of f of tau g of t minus tau d tau. So t is the original variable, and notice in the integral I have the variable tau. This is basically a dummy variable or a placeholder. That's the variable of integration, and when we complete this integral and apply our fundamental theorem of calculus and evaluate upper limit minus lower limit, the final result is going to be a function of t. So the reason that we're learning the convolution property is because it's going to simplify, believe it or not, some of our Laplace transforms. So in this first section, we're just learning how to execute this operation, and then we'll see how it applies to solving initial value problems. Now, one thing you need to know about convolution is that it is a commutative operation. Thus, f star g is equal to g star f of t. So you can apply those functions in either order and still end up with the correct answer. So let's see if we can apply this operation to two functions. Example 1. Find f star g of t given f of t equals e to the t and g of t equals sine of t. So f star g of t, the convolution of e to the t and sine of t, we could also write it like this, by the way, e to the t star sine of t, or e to the t convolved with sine of t. Applying our definition, this is the integral from 0 to t of f of tau. Now, f is my first function. Our first function is e to the t. I'm going to write it e to the tau times g of t minus tau. G is going to be sine. So we're going to do sine of t minus, and again, that's Greek letter tau. And our variable of integration is tau. One challenge of this formula is distinguishing in your own handwriting the difference between t and tau. Now, again, the variable of integration is tau, so when I integrate, I will treat t as if it is a constant. Now, we have the product of an exponential and a trig function here, so to integrate, we're going to use IBP, integration by parts. Let's choose u equal to sine of t minus tau, so that du, the derivative of sine with respect to variable tau, the derivative of sine is cosine of t minus tau, times, according to the chain rule, the derivative of the argument. The argument is t minus tau, the variable there is tau, so I'm going to multiply this by a -1. d tau. Then from integration by parts, dv is going to be everything else that's left in the integrand, e to the tau d tau. Integrating on our way up, we end up with e to the tau. Applying this to our integral, we have u times v. I'm going to write that e to the tau times sine of t minus tau. U times v, this needs to be evaluated from 0 to t, minus the integral of v du. That's going to be e to the tau times negative cosine of t minus tau d tau. So notice the negative from the du I used to cancel out the minus from integration by parts to simplify. Let's go ahead and apply the upper limit and lower limit there to our first term. And then notice we're going to need another round of integration by parts on that second term. So plugging in our upper limit, we have e to the t times sine of t minus t. Remember, the variable of integration was tau, so I'm plugging my limits, 0 and t, in for tau. Okay, upper limit minus lower limit, e to the 0th times sine of t minus 0. Now, let's work on our second integral, again using integration by parts. So this time, I'm going to choose u equal to cosine of t minus tau. Du then is the derivative of cosine, which is negative sine, times t minus tau times the derivative of the argument, which is negative 1 d tau. Then again, we can choose for dv, e to the tau d tau, and v is e to the tau. So applying this integration by parts to that second integral, we have u times v, that's e to the tau, cosine of t minus tau, evaluated from 0 to t, minus the integral of v du. That's 0 to t, e to the tau, sine of t minus tau d tau. Now notice we can go ahead and simplify the first three terms, and then we have reproduced our original integral that we began with. So we're not going to need to do another round of integration. We will have to solve for that integral algebraically. So working on or continuing our simplification, notice over here in the first term we have e to the t times sine of 0. Sine of 0 is equal to 0. So we have obliterated that first term. On our second term there, we have e to the 0th, which is 1, times sine of t, and we have a negative out front. So that's negative sine of t, plus, working on our third term here, evaluating upper limit minus lower limit, we have e to the t times cosine of t, minus lower limit, e to the 0th, cosine of t minus 0. And then again, we're not going to do anything with this integral because that was our original problem. Okay, finishing out our simplification here, we have negative sine of t. In this spot, we have cosine of 0. Cosine of 0 is equal to 1. So this term becomes e to the t. And next, we have e to the 0th, which is 1, times cosine of t. So that term becomes minus cosine of t. And I'm just going to string this little fella along until the next step. Okay, now let's look at the context of our original problem. We started with e to the t convolved with sine of t. By definition, this is what this means, and we have whittled it down to this. Okay, so I'm going to rewrite the equation like so. The integral from 0 to t, this is the original problem, we have found is equal to negative sine of t plus e to the t minus cosine of t minus the integral from 0 to t e to the tau sine of t minus tau d tau. Okay, so this term and this term are like terms. So I'm going to add that integral to both sides and combine like terms. So we have 2 times the integral from 0 to t, e to the tau, sine of t minus tau d tau, equals all these leftovers over here. Now, I prefer to lead with a positive, so I'm going to put the e to the t in front. Just makes it a little more readable. By the way, we do not need a plus c. So, solving for this integral, we can multiply both sides by 1/2, and we end up with e to the t minus sine of t minus cosine of t. And that is the convolution of e to the t with sine of t. That was pretty exciting, pretty intense. So we are learning a new operation called convolution, and you may feel a little convoluted at this point. But the reason that we're learning this is because it's going to simplify our Laplace transforms. So the focus here is to understand that when I see this binary operator, this is what I carry out. Tricks to understanding this method: realize that you're integrating with respect to the variable tau, but when that operation is complete, your result will be a function of t. So in this case, e to the t convolved with sine of t gives us this function of t over here. Okay? Now, what are we going to do with this? Let's look at the next theorem. If f of t and g of t are piecewise continuous for all t greater than or equal to 0, and the absolute value of f of t and the absolute value of g of t are of exponential order c as t approaches infinity, remember those were necessary and sufficient conditions for the Laplace transform to exist, then the Laplace transform of the convolution, f of t star g of t, exists for s greater than c, and the following are true. Now, here is why we learned the Laplace transform. The Laplace transform of f of t convolved with g of t is equal to the Laplace transform of f of t times the Laplace transform of g of t. So if on this side of things we have the operation convolution, then on this side of things we're looking at the product of their transforms. In reverse, if we're looking at the inverse Laplace transform of the product of two functions of s, then we're going to end up with the convolution of their inverse transforms. So the idea is, let's look at the inverse direction. If I have the product of two functions of s, and I can find both of those functions on the table and individually find their inverse transforms, that is, I take big f of x and I find little f of t from the table, I take big g of s and I find little g of t from the table, I inverse transform each function separately, then I will convolve those two functions and I will have executed what started out as a really tough inverse Laplace transform and made it pretty simple. Okay, maybe convolution is not that simple, but this is how it works. Now, one thing I want you to be aware of, this warning right here. The Laplace transform of the product of two functions, f of t and g of t, is not equal to the product of their Laplace transforms. Okay? You already know this fundamentally with derivatives and integrals. For example, the derivative with respect to x of the product of two functions of x is not equal to the derivative with respect to x of f times the derivative with respect to x of g. Okay, make sure you write not equals. We know that if we start with the product of two functions and we want to find the derivative, we have to apply something called the product rule, right? Also, similarly, the integral of the product of two functions of x is not equal to the product of their integrals. We're stating the exact same thing with Laplace transforms. All of these operators, the derivative, the integral, and the Laplace transform operator, they all work the same way. So if I'm trying to transform the product of two functions, I am not going to find the product of their transforms. In the same way that if I'm trying to differentiate the product of two functions, I am not going to find the product of their derivatives. Instead, we're going to follow the properties stated in the theorem. So let me clean this up so we can see that theorem. we're going to use this property. And again, think of it like a real fancy product rule. If you're going to find the derivative of the product of two functions, you've got the product rule to do it. If you're going to find the Laplace transform of the convolution of two functions, here's the rule for carrying that out. Okay, enough talk. Let's give it a try. Sometimes examples make all of these complicated explanations make sense. Example 2. Find the inverse Laplace transform of 1 over s squared plus k squared squared using convolution. This is an exercise to help you understand these properties, but let's flip over to our table of Laplace transforms, and I want you to know we already have this formula. It's right here. Now you may wonder, how did they come up with this formula? I know that keeps you up at night. You stay up late thinking, how did they get all those formulas? Well, we are about to prove this particular formula. So we're going to start with a function of s. We're going to use our new convolution property to establish this relationship. Okay? Find the inverse Laplace transform. What we want to do is view this as a product of two functions. Okay? So I'm going to start with a couple of definitions so I can view that as a product. We're going to say that both big f of s and g of s are the same function. That is 1 over s squared plus k squared. Okay, so I recognize f of s times g of s gives me this function right here. So I'm going to view that as the product of two functions of s. Okay? Now, big f of x inverse transforms into little f of t. And big g of s inverse transforms into little g of t. Right? And they're going to be the same. So let's find 1 over s squared plus k squared on our formula. 1 over s squared plus k squared. We're going to be looking at this formula right here. The only thing we're missing in our problem is the k on the top. We have a 1 in our numerator. So when we inverse transform, we'll multiply sine of kt by 1 over k. So this is going to be 1 over k times sine of kt. And that was one of the properties that we practiced in section 4.1. So what I'm doing is looking at the original function as the product of two functions of s. Let me be as clear as possible here. The original function, 1 over s squared plus k squared squared, we are viewing as 1 over s squared plus k squared times 1 over s squared plus k squared. And we want to find the inverse Laplace transform of this product. The inverse Laplace transform of this product is going to be the convolution of the inverse transforms. Well, each individual factor here has the same inverse transform. That's what we discovered here. So to find the inverse transform of this product, we need to find the convolution of 1 over k sine of kt with itself. Okay, let's write that down so that we are clear where we're going. The inverse Laplace transform of 1 over s squared plus k squared times 1 over s squared plus k squared is going to be the convolution of the individual inverse transforms of each factor. So this is going to be 1 over k sine of kt convolved with 1 over k sine of kt. Okay, so the order of operations, I find the inverse transform from the table of each individual factor, and then I'm going to convert from multiplication on the s side into convolution on the t side. So all we lack now is to execute the convolution of these two functions, which you know is not really an easy process. Now to save room, I'm going to slide my equal sign over here. Notice we have 1 over k as a constant coefficient of each function. I'm going to multiply those together and factor those in front of our integral. So we have the integral from 0 to t. Now remember the definition of convolution. We have f of tau, g of t minus tau. So I'm going to evaluate the first function at tau and the second function at t minus tau. So this is k of t, k times t minus tau d tau. We may want to write that a little clearer. Sine of k tau times sine of kt minus k tau d tau. Now we are integrating the product of two sine functions. And if you'll remember, you learned product to sum formulas probably in your Calculus 2 class. So you very likely do not have these memorized, but you should be familiar with them, be able to locate them. So let me remind you the product to sum formula for sine of A times sine of B. This is equal to 1/2 times cosine of A minus B minus cosine of A plus B. So I'm going to apply this product to sum formula so that I'll be able to split that integral into two distinct integrals. Okay, here we go. Let's give it a try. 1 over k squared times the integral from 0 to t. And we're going to multiply by a factor of 1/2. Let's go ahead and sneak that in front of the integral. We'll get the constant out of the way. And we're going to have cosine of the first argument minus the second argument. So I have first argument minus the second argument. That's going to give us, let's see here, k tau minus kt plus k tau. So that's 2k tau minus kt. Continuing with our formula, minus cosine of A plus B. When we add those two arguments, we just get k tau d tau. So that split our product into a sum. So now we can take our integral as two distinct separate integrals and find those antiderivatives. So each integral is going to have this coefficient 1 over 2k squared. And each one gets the integral from 0 to t. So here we're just priming the integrand to make it easy to find the antiderivative. Okay, now that everything is split up, we're going to handle each integral individually. So let's work on our first integral. We've got this coefficient 1 over 2k squared. And now we want to find the antiderivative of cosine, oops, I forgot a d tau, sneak that in there. Antiderivative of cosine of 2k tau minus kt dt. So we're going to recognize first that when we integrate cosine, we get sine. So we're going to have sine of the argument, and we divide by the derivative of the argument with respect to tau. The derivative of that argument with respect to tau is 2k. Then we will evaluate this from 0 to t. Okay? Working on our second antiderivative, we're going to integrate cosine of kt with respect to tau. Now be really careful on this one. This one's tricky. My variable of integration is tau, and my argument kt is then constant. So cosine of kt is constant with respect to tau. So to integrate a constant, I end up with the constant times the variable tau. So I'm going to put the tau over here, variable times constant. Okay, and we're going to run that from 0 to t. All right, so again, we integrated a constant with respect to the variable tau, so we end up with that constant times tau. Now, let's go back and apply our upper and lower limits. Working on our first term, we have 1 over 2k squared, and notice we have a 2k in the denominator to the right, so let's go ahead and multiply those together. 1 over 4k cubed. Then we're going to have sine of, we're plugging in our upper limit t. Don't forget our variable of integration was tau, so we plug our limits of integration for tau. So we have 2kt minus kt, there's the upper limit, minus plugging lower limit 0 in for tau. we're going to have sine of 2 times k times 0, which is 0, minus kt. So there's upper limit minus lower limit for our first term. Second, we have 1 over 2k squared times plugging upper limit t in for tau. We have t cosine of kt minus 0 times kt, which ends up being 0. Okay, now let me clear up some space here so we can work on simplifying. Okay, moving on up here. Working on our simplification, we have 1 over 4k cubed. Notice the argument here, 2kt minus kt. That just gives me sine of kt. And remembering that sine is an odd function, sine of negative x equals negative sine of x, right? We can simplify that to be plus sine of kt. And then our second term, 1 over 2k squared t cosine kt. All right, continuing our simplification process, inside here we have 2 sine of kt. We can cancel the 2 with the 4 out here, so we have 1 over 2k cubed sine of kt minus 1 over 2k squared t cosine kt. Now, it's looking very similar to the formula that we are trying to establish, but notice in this formula, they factored the 1 over 2k cubed out to the left. So let's do that, and we'll see if our formulas match. So I'm going to factor out 1 over 2k cubed. That leaves behind of our first term, sine of kt. Now, the only thing missing in this denominator is a factor of k. So I'm going to multiply the top and the bottom by k, and we end up with kt cosine kt. Okay, so let's compare this to the result. Sine kt minus kt cosine kt with the correct factor outside. So we have just proved a formula from the table of Laplace transforms. We did it using the convolution property. So try to get the big picture. We started out with the product of two functions. We inverse transformed each individual function, each individual factor, and then on this side of things we found the convolution. And that led to the inverse Laplace transform that we were looking for. All right, this is very detailed. It's going to improve your algebra. It's going to improve your calculus and assist you with solving differential equations. We're going to consider 2 more properties that are helpful in this section, differentiation of transforms and integration of transforms. So let's talk about differentiation of transforms. If f of t is piecewise continuous for all t greater than or equal to 0, and the absolute value of f of t is less than or equal to m e to the ct, that just means it's of exponential order and its Laplace transform exists, then here's the heart of the theorem. The Laplace transform of negative t times f of t equals big F prime of s for all s greater than c. So if you'll remember in section 4.3, we said if we have a special factor over here, e to the at, that causes an effect in the variable s. Remember, it was a translation on the s-axis. So this is saying if I have the presence of the factor negative t right here, then I'm going to go ahead and transform little f of t like I normally would to get big F of s. But because of the negative, I'm going to find the derivative of that transform. So there's an important order of operations that's implied there. And similarly, going the other way to get little f of t, which is the inverse Laplace transform of big F of s, I can inverse transform the derivative and then multiply the result by negative 1 over t. Now, why would I want to do that? Sometimes it's easier to locate a function that is the derivative of an original on the table than the original. So, for example, when you have a natural log function, natural log does not appear anywhere on our table of transforms and inverse transforms, all of those functions are algebraic. Because the derivative of natural log is algebraic, we can employ this formula to do that. Okay? Also, in general, anytime you have one of your elementary functions f of t multiplied by a power of t, then you can look up little f of t on the table, find the Laplace transform, find the nth derivative of that Laplace transform, and then multiply by -1 to the nth power. Okay, we'll do examples of both of these. Keep in mind, when you get ready to do your homework, or even when you get ready to take your test, you will have the table of transforms and all of the formulas for Laplace transforms with you. So your job is to know, how do I use these formulas? If I can look at it, how do I properly execute it? So let's give it a try. Let's actually do example 4 first. So I'm going to come over here and work this one. As I mentioned before, natural log of a function of s does not appear anywhere on the table of Laplace transforms and inverse Laplace transforms. But because we know that the derivative of the transcendental natural log function is algebraic, we are going to make use of that to find the inverse transform. So the inverse Laplace transform of some function of s, like what we have here, is -1 over t times the inverse Laplace transform of its derivative. Let's write all that down. The inverse Laplace transform of, this is our big F of s, is equal to -1 over t times the inverse Laplace transform of the first derivative of our function. So I'm going to write it as d over ds of natural log of 1 over s. I hope you're having fun. You're thinking, when does the fun begin? It begins right here. So we have -1 over t, and we're finding the inverse Laplace transform of the derivative of the function. Why? Well, let's execute the derivative and you'll see. Okay, the derivative with respect to s of natural log of 1 over s. Remember, we put the argument in the denominator and the derivative of the argument in the numerator. Let's simplify that complex fraction. We have s times -1 over s squared, which gives us -1 over s. Okay, now, since the derivative of our original function is algebraic, it should be on the table. So I'm going to search the table for 1 over s. Here it is right here. The inverse Laplace transform of 1 over s is 1. So the negative here times this negative makes a positive. The inverse Laplace transform of 1 over s is 1. So we end up with inverse Laplace transform 1 over t. So the purpose of this formula, the second formula up here, if the function does not appear on the table, but possibly its derivative does, then we can inverse Laplace transform the derivative and then multiply by -1 over t. Okay, let's try example 3. Example 3, we have the Laplace transform of a power of t squared times hyperbolic sine of 2t. So we are multiplying by a power of t. So what we're going to do, looking at how do I use this formula, first I'm going to transform little f of t into big F of s, but then I'm going to need to find a derivative. So the Laplace transform of t squared times hyperbolic sine of 2t, following our formula, is going to be -1 to the second power. Remember, whatever power of t is, we're going to use it right here, times the second derivative, I'm going to use a differential operator, d squared over ds squared, times the second derivative of the Laplace transform, this is big F of s, of hyperbolic sine of 2t. Okay, so again, when you do your homework, when you take your test, you will have all of the formulas before you. Your job is to figure out, how do I interpret and correctly apply those formulas using the right order of operations. So let's continue working on this. Negative 1 squared is positive 1. So we need the second derivative of the Laplace transform of hyperbolic sine of 2t. Let's find hyperbolic sine on our table of transforms. We have hyperbolic sine of 2t. I'm going to be using this transform. Rk is 2, so we're going to get 2 over s squared minus 4. So in our box, we have 2 over s squared minus 4. So notice I just transformed hyperbolic sine of 2t, and the presence of this t squared is causing me to do all the other operations according to that formula. So we need to find the second derivative of 2 over s squared minus 4. I'm going to think of that function as 2 times s squared minus 4 to the negative 1. So we'll find our first derivative, and then we'll need to find another derivative. The first derivative is negative 2 s squared minus 4 to the negative 2 times 2s. And then we need to differentiate this. So notice I found one derivative and decreased the order of my operator, right? So we have one more derivative to find. I'm just simplifying here. Negative 4s times s squared minus 4 to the negative 3. You can either do the product rule or the quotient rule, whichever one you prefer here. I think I'm going to go back to a quotient so that I won't have to worry about a common denominator after I do the product rule. Okay? So our quotient rule begins by squaring the denominator and then leading with that term in the numerator. Multiply by the derivative of the numerator minus derivative of the denominator times the numerator. And then we will simplify. Both of the terms in the numerator have both a negative 4 and an s squared minus 4, so I'm going to factor that out. Factoring both of those terms out of the first term, we have a 1 left over, and then we have minus 3 times s squared minus 4. Okay? Now that it's factored, we're going to be able to reduce one of those s squared minus 4 factors with the denominator. Okay, let's go ahead and do that in red. I'm going to cancel this, make that a 5. So we have negative 4 times. Inside brackets there, we have 1 minus 3s squared plus 12. So let's call it 1 plus 12 is 13 minus 3s squared over s squared minus 4 to the 5th power. And that's a done deal. So what's the big picture on this one? The big picture is we were transforming an ordinary function multiplied by a power of t. If we have the presence of the power of t, any power of t with an elementary function, we first transform that elementary function ignoring the t squared. And that's what we did right here. Okay, then to account for the t squared, whatever the power of the t is, we're going to find that order of the derivative. And then we proceeded there just to find the first and second derivatives of that function of s. And then we have the transform, the transform of the function of t. So we have arrived at example 5. Example 5 will justify why we are learning these difficult, complicated Laplace transform formulas. Look at the differential equation that we're going to solve in example 5. Find a non-trivial solution to tx double prime plus 4t minus 2x prime minus 13t minus 4x equals 0, subject to my favorite initial conditions, x of 0 equals 0, x prime of 0 equals 0. So I want you to observe this is a second order linear homogeneous differential equation with, what do you notice about the coefficients? Non-constant coefficients. So we have finally arrived at a higher order DE that does not have constant coefficients. Laplace transforms are perfectly suited for just such a problem. So we are going to solve this differential equation using the Laplace transform. So we need to know, how do we transform those derivatives? We'll review those formulas here in a minute. And we're going to employ our new derivative formula. Okay, so all of that knowledge is coming together for the purpose of this class, which is solving a differential equation. So first of all, let's remember our formulas. Okay, recall the Laplace transform of the second derivative of little x of t is s squared times big X of s minus s little x of 0 minus x prime of 0. This was section 4.2, right? Also, the Laplace transform of x prime of t is s big X of s minus little x of 0. Distinguish between big X, the Laplace transform, and little x, the initial condition. And the new formula we just learned, we haven't practiced this one yet, but we practiced the generalization of this. Negative t f of t under Laplace transform gives us big F prime of s. So we're going to apply all three of those formulas to solve this differential equation. Okay, so let's transform the given differential equation term by term. So I'm going to start with the Laplace transform of t x double prime. First of all, notice I am multiplying by t. If I multiply a function by t, then I'm going to find the first derivative of its transform. And in particular, this term is multiplied by positive t, so I'm going to transfer that negative to the other side of the transform. Okay, again, if I have t to the power of 1, that means I'm going to find the first derivative with respect to s of the transform of the function. So this part is accounted for with negative right here and first derivative. Okay, now the transform of x double prime, and I'm going to leave off this argument, is s squared big X minus s little x of 0 minus little x prime of 0. Phew, we made it through term number 1. Next, let's work on term number 2. Now, I'm going to treat that as, I'm going to distribute the coefficients 4tx prime minus 2x prime. Okay, so let's work on transforming this. So first of all, I have a 4, so I'm going to carry that 4 out in front of all of my operators. Then I'm multiplying by t to the first power. Well, in our formula, we have a negative t. So let's go ahead and account for that negative right here. And then, because we have t to the first power, we're going to multiply by the first derivative of the Laplace transform of x prime. The Laplace transform of x prime is s big X minus little x of 0. Okay, then we have minus 2 times the Laplace transform of x prime, no factor of t there. So the Laplace transform of x prime is s big X minus little x of 0. Okay, moving on to our second term, let's go ahead and distribute like we did before. Let's call that 13tx minus 4x. So we're working on transforming 13t times x. So we have a 13, we're going to factor that out. We have the presence of the factor t, not negative t. So we'll have to filter that negative to this side. And remember, when we multiply by t, that means I need the first derivative of the transform. The transform of little x of s is big X of s. Minus 4 times the Laplace transform of x, which is just big X. And on the other side, the Laplace transform of 0 is 0. Okay, we are making headway. We need to go back and apply our initial conditions and then execute derivatives. Now, here's why these are my favorite initial conditions. Little x of 0 is 0, so this term goes away and this term goes away, and a couple of other spots as well. So 0 initial conditions really simplify our algebra. So I'm going to take a step and clean this up. We need the negative first derivative with respect to s of s squared big X, all of my x's are now going to be big X's, minus 4 times the derivative with respect to s of s times x, minus 2 s x, no derivative there, minus 13 times the derivative with respect to s of big X, minus 4 big X equals 0. You know, the best thing about lecture videos is that you can pause me and you can go back and listen again if you get lost in the details. So please feel free to do that at any time. On our next step, we are going to execute these derivatives. Now, one thing I want you to remember is that big X is a function of s. We have written it without the argument to make it readable, but it is a function of s. So on this first term, when I find the negative first derivative of s squared x, I have to realize this is a product of two functions of s. And so I'm going to have to use the product rule to do that. So we have negative times, now applying our product rule, we have the first function s squared times the derivative of the second, and that's x prime of s. Again, I'm leaving the argument off, plus the derivative of the first function 2s times the second. Okay, we're going to apply the product rule on s times x as well. We have the first function times the derivative of the second, plus the derivative of the first, which is 1 times the second. Then we have ordinary 2sx, no derivative to calculate there, minus 13 times the derivative with respect to s of x, that's x prime of s, minus 4x equals 0. Now, let's group our x prime terms together and our x terms together. So I'm going to distribute negative s squared x prime minus 2sx minus 4sx prime minus 4x minus 2sx minus 13x prime minus 4x equals 0. So again, let's combine coefficients of our x prime terms. So coefficients of x prime include negative s squared minus 4s minus 13. And coefficients of x include negative 2s minus 4 minus another 2s minus 4 times x equals 0. Okay, let's clean up that second set of parentheses to get negative 4s minus 8 times x equals 0. Now, believe it or not, we are back to chapter 1. We have to recognize what we have here. Notice we have a first order differential equation, x prime. We can think of that as dx over ds. We've got the variable x, that's our dependent variable. We have the independent variable s. This is actually a separable differential equation. To understand this, maybe a different form of notation would help. So I'm going to do two things on this step. I'm going to change that x prime into dx over ds, And I'm going to move this term to the other side. So we have 4s plus 8 times x. Again, we can solve this with separation of variables. That is, I'm going to get all my x's on the left side, and I'm going to get all the s's on the right side. Again, back to chapter 1, we just have to recognize the problem, right? So dividing both sides by x, we can write that as 1 over x dx. And moving all of our s's to this side, we've got 4s plus 8 over there now. We're going to divide by negative s squared minus 4s minus 13, and we're multiplying by ds. So we have separated our variables. So remember, to solve by separation of variables, we're going to integrate both sides, the left side with respect to x, and the right side with respect to s, at least in execution. So on the left side, we end up with the natural log of the absolute value of x, and that's still big X, by the way, big X of s. And working over here, we have to figure out our method of integration. I'm thinking we can handle it with a u substitution. What do you think? Let's try u equals negative s squared minus 4s minus 13. And then du would be negative 2s minus 4 ds. If I multiply that by a negative 2, I would get 4s plus 8 ds. So we can think of this as the integral of 1 over u times 2 du. So when we integrate, on this side, we have the natural log of the absolute value of x. Over here, we have 2 times the natural log of the absolute value of u, which was negative s squared minus 4s minus 13. And for good measure, let's get a plus c. So let's convert to exponential form. Okay, we're going to take base e with this exponent, that whole right side, and set it equal to the argument. So our argument, big X of s, is going to be e to the exponent 2 times the natural log of the absolute value of negative s squared minus 4s minus 13 plus c. And as we have done so many times before, we know that that constant c, if we separate that into a product, I have a feeling I'm going to need all this space, so let me scoot up a little further. So we have x equals e to the 2. Now let's take that 2 and move it as an exponent on the argument of the natural log. We'll call that squared, and then e to the c. E to the c is just a constant, so we can move that. We'll call it nu c. And then e to the natural log is simply the argument, negative s squared minus 4s minus 13 squared. Okay, let me backtrack just a bit. Did anyone catch my mistake? Coming way back over here, that was supposed to be negative 2. I apologize. I'll correct it here. So this becomes exponent negative 2. Okay, so let me rewrite this as clear as possible. Big X is c times negative s squared minus 4s minus 13 to the negative 2. Or if you wanted to write that as a fraction, big X is c over negative s squared minus 4s minus 13 squared. Okay? So the good news is we have found big X, but we're looking for little x. So little x, the solution to our original differential equation, is the inverse Laplace transform of big X. So next we need to work on inverse transforming big X of s. So our solution that we're after, little x of t, is the inverse Laplace transform of big X of s, which we have found. So to solve for x of t, we need to find, let's go with c times the inverse Laplace transform of 1 over negative s squared minus 4s minus 13 squared. So our problem now has been reduced to finding the inverse Laplace transform of this function. So we're going to have to apply a little bit of algebra. Let's factor a negative out of the bottom, and I'm feeling like we're going to need to complete the square. So we have c times the inverse Laplace transform of 1 over, factoring our negative out of the bottom here, we have negative 1 times s squared plus 4s plus 13. All of this is squared. Squaring that negative 1 coefficient makes it positive. So we have c times the inverse Laplace transform of 1 over s squared plus 4s plus 13 squared. Let's go ahead and complete the square with that trinomial in the denominator. So we have s squared plus 4s. 4 completes the square there. We originally had a 13, and I'm going to subtract the 4 that I just introduced back off, not to change the original function. So we have c times the inverse Laplace transform of 1 over, factoring, we get s plus 2 squared plus 9 quantity squared, which is one of our basic Laplace transform formulas. So let's find that on the table. Do notice we have a translation on the s-axis. So I'm going to come over here and notice we're going to use the formula that we derived earlier. We have this formula right here. Okay, I've got a 1 in the numerator. S squared plus k squared squared. Here is the inverse Laplace transform. Okay, first of all, let's do the easy part. Let's figure out what k is. Whatever constant squared I have right here, we can identify k from. So because we have a 9 in that spot, we know k is going to be 3. Okay? The second thing that we need to be aware of is we have a translation on the s-axis. So this is going to cause that factor e to the at in our inverse transform. So continuing, our inverse transform is going to be start with the c, then we're going to have the presence of e to the negative 2t. That's because of the translation. And once we take care of that translation, then the inverse transform comes directly from the table. We have 1 over 2k cubed to begin with. So on our work, we have 1 over 2 times k, which is 3, to the third power. Okay, looking back at our formula, sine of kt minus cosine kt. So we have sine of 3t minus 3t cosine 3t. Okay, let's clean it up. We have 1 over 2 times 3 cubed. 3 cubed, you know what let's do? This is a constant, this is a constant times a constant is a new constant, times e to the negative 2t times sine of 3t minus 3t cosine of 3t. So congratulations, you have just solved a higher order differential equation with non-constant coefficients using Laplace transforms. Now that is a pretty beefy problem. We had to know a lot of techniques in order to do that. First of all, we had to know how do you transform a differential equation. We studied that in section 4.2. We had to know what happens if I multiply by a power of t. We learned that today. We transformed term by term and simplified as far as possible. And then we had to recognize what's the new nature of our problem. We transformed it into a linear first-order differential equation that we were able to solve by separation of variables. Once we solved that by separation of variables, then we had to find the inverse transform to get the original solution. To do that, we had to be able to complete the square. We had to be able to recognize translation on on the s-axis and how that affects the solution on the t-axis. So, man, that is a problem that you should be proud of. Okay, I know this is a lot of information, so pause the video, go grab a glass of coffee or tea or something, and come back. Or if you're ready to go, we've got one more topic to talk about in this section. We've done differentiation of transforms, so you know it's coming. Let's talk about integration of transforms. So here's the theorem. Suppose that f of t is piecewise continuous for all t greater than or equal to 0, that the limit as t approaches 0 from the right of f of t over t exists and is finite, and that the absolute value of f of t is less than or equal to m e to the ct as t approaches infinity. All right, a lot of details. Don't panic about that. Those are hypotheses that must be satisfied for this theorem to work, and for the problems that we're working, it's going to work. So we are going to practice applying the formula. When you get into your more advanced differential equations, you can learn how to take care of those hypotheses. Now remember, this is elementary differential equations, right? The title of our book is Elementary Differential Equations. So our focus is how do we learn this formula? The formula is the Laplace transform of little f of t divided by t. Hey, we know what to do if we multiply by t, right? Now we're talking about what do we do if we divide one of those elementary functions by t. We're going to evaluate this as the integral from 0 to infinity of f of sigma d sigma. Sigma is a lowercase Greek letter like the tau. It's functioning as a dummy variable here. So if I divide an elementary function by t, I'm going to find the integral of its Laplace transform. On the other side, if I'm trying to find little f of t as the inverse Laplace transform of big F of s, then I can multiply the inverse Laplace transform of the integral of the big F of sigma by t. Okay, we're going to practice this both directions. Remember, your focus is to interpret these formulas and to understand what to do, not necessarily to memorize these formulas. So let's try the first direction. We have the Laplace transform of sine of t divided by t. First thing I want you to notice in this formula is that little f has turned into big F. That means I have found the Laplace transform of little f. And I'm not looking at this denominator at the point, right? So let's take care of that first. I want you to note that the Laplace transform of sine of t is equal to, pop over to your Laplace transform formulas. Find the formula for sine of kt. Rk is going to be 1. So the Laplace transform is 1 over s squared plus 1. Okay? That is big F of s, right? So I took little f of t. This is little f of t. Let me get a different color so this is clear. This is little f of t. And this is big F of s. Okay? So that part's taken care of. Now, let's work on the whole thing. The Laplace transform of sine of t over t, according to the formula then, is the integral from 0 to infinity of big F of sigma. So all I'm doing here is using my big F of s that I found and replacing that s with a sigma, like a dummy variable. So I need to evaluate the integral from 0 to infinity of 1 over sigma squared plus 1 d sigma. Now, hopefully you recognize that the integral of 1 over sigma squared plus 1 is inverse tangent or arctangent of sigma, and we need to evaluate this from 0 to infinity. That's the limit as b approaches infinity of inverse tangent of sigma from 0 to b. Applying the fundamental theorem of calculus, we evaluate this as the limit as b goes to infinity of inverse tangent of b minus inverse tangent of 0. Thinking about the unit circle or thinking about the graph of inverse tangent, The limit as b goes to infinity of inverse tangent of b is pi over 2. And, oh, hold on. Pause. I have an important typo. I so apologize. I just caught it right here. Go back to the formula. I'm so sorry. That lower limit should be s. So this lower limit should be s here. Please correct that on your notes. That's a little bit important. That should be s. Otherwise, we're not going to get a function of s, right? Minus inverse tangent of s. So pi over 2 minus inverse tangent of s. So you might be wondering, how did I figure out that the limit as b approaching infinity of inverse tangent of s is pi over 2? Here's the simplest way to think of it. If we graph inverse tangent, it's got horizontal asymptotes at negative pi over 2 and pi over 2. So as the argument approaches infinity, the function levels out at pi over 2. Okay? And pi over 2 minus inverse tangent of s is perfectly acceptable, or you can apply a trig identity and call that inverse tangent of s. So that's pretty exciting. You found the Laplace transform of sine of t over t, and you ended up with an inverse trig function. One last problem for this section. We're going to go in the opposite direction and find the inverse Laplace transform of 2s over s squared plus 1 squared. So what we're going to do in this case is, looking at the opposite direction, we're trying to find little f of t. We're going to simplify the process a bit. So we're going to multiply by a factor of t and find the inverse Laplace transform of the integral of this function. So to find the inverse Laplace transform, we're going to multiply by t and find the inverse Laplace transform of the integral from, make sure you get lower limit s there, s to infinity of big F of sigma. So I'm just going to change those s's to sigmas. And you might think, why would we want to do that? Well, this is a very easy integral to evaluate. So notice I can make a u substitution. U is sigma squared plus 1. du lives up there in that numerator, 2 sigma d sigma. So evaluating our integral, we have t times the inverse Laplace transform of the integral from, now I'm changing variables here, so I'm going to put stars for a minute, okay? I'm not going to update my limits. We'll come back and pick up our original variable. But we have u to the negative 2 du. This becomes inverse Laplace transform. Integrate, we're going to get u to the negative 1 over negative 1, or negative 1 over u. And we're going to run that between two limits, but not until I go back and pick up the original variable. The original variable, u, remember, was sigma squared plus 1. So I'm going to evaluate this from s to infinity. Okay? So, applying our limits of integration there, we have the inverse Laplace transform of the limit as b approaches infinity of negative 1 over sigma squared plus 1 from s to b. Applying our upper limit and lower limit, we have the limit as b approaches infinity of negative 1 over b squared plus 1 minus a negative 1 over s squared plus 1. As b approaches infinity, this first term is going to go to 0. So we have t times the inverse Laplace transform of 1 over s squared plus 1. Okay, looking at our table of Laplace transforms, 1 over s squared plus 1, we're picking on this sine formula, is sine of kt, or sine of t. So our inverse Laplace transform then is t sine of t. Okay, this has been a pretty intense section. This video is available if you need to go back and re-watch it and rework these problems, but keep in mind, your job is to recognize what the formulas are and how to apply them, not necessarily to memorize them because they are pretty intense formulas. They look simple, they're little one-liner formulas, but they imply some complicated operations. So best of luck to you as you continue studying Laplace transforms.